Okay, everyone, welcome back. This is that second lesson on perfect squares, perfect cubes, and roots. This is going to become super important in the next one when we start to talk about exponents, integral exponents, rational exponents, that sort of stuff. And it comes back in every single math course that you're probably going to take in high school. So this is where it really starts. And again, in the description box below, you'll see the two links, one with the blank copy of this presentation, and the second one has the filled out solutions manual. So I'm not going to do every single example in here. As you'll see, there's going to be a lot of them. So I'll pick and choose a couple, but in the solution key, I'll give you everything. So if you do try out the ones on your own that we haven't done, at least you have that available to you, okay? So here we go. 25 is a perfect square, and 5 is its square root because. So there has to be some statement that we could fill that in to make it true. So there's a relationship between something being a perfect square and something being a square root. Now, we can relate those two numbers by saying that if I take that square root, which is 5, and I square it, so take 5 and multiply it by itself. We did kind of talk about that in the last video as well. If I do that, that's going to give me my original value of 25. Okay, now we'll put that into words. So we'll define actually what a perfect square is here. And we're going to say it's the product of a rational number multiplied by itself. Okay, and a rational number is just something that can be written rationally. So we can write it as a fraction. So 5 in this case is going to be our rational number. Now I can write that as a fraction by doing 5 divided by 1. Okay, now that fraction, if I multiply it with another identical fraction, 5 over 1, you're going to get the value of 25 over 1, which again is going to give you that perfect square number. Now, the other side of this, we have to kind of think about this going backwards. What if I start with the original number and try to find the value that when I do square it, I get my original? And that's what we're going to call the square root. Okay, and we're going to say that it is a value. Sorry, I have the definition here. So a value that can be multiplied by itself to give the original number. Okay, so if you were asked to find the square root of a number, let's say 36, you were asked to find the square root of that, you'd be looking for a value that you could multiply by itself to give you that value of 36. So for example, it couldn't be 12 and 3 because you're not really multiplying either of those by themselves. You're multiplying them by two different things to give you 36. Okay, so while 12 and 3 are factors of 36, they can't be the square root because remember, it has to be the same number. Okay, we're going to list out the first 15 perfect squares down below. Now, I know 15 seems like a lot, but they're going to be pretty common throughout your next couple of years in math, so you'll see them very, very often and be able to recognize them right away. It helps when you do go to factor some things as the values get larger. So I'm going to create just a little table here. It's going to help us organize it. Okay, and we're going to say that we have our x values on top, and then what they're going to be underneath. So I'm just defining them as variables. Okay, and we'll give ourselves a couple columns. We're going to need quite a few. I don't know if I've got the right amount. I might have to add some, but that's okay. So we need the first 15. So 1, 2, 3, 4, 5, 6, all the way. And I'm too short. So there's 14, and there's 15. So underneath, we're going to put their squares. So 1 multiplied by itself will give us 1, and follow the pattern all the way down. So 2 times itself will give us 4, and 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 14 squared is 196, and 15 is 225. So these are going to be the ones that are the most common that you'll see come up. Any numbers that get larger than 15 squared, it doesn't necessarily add to the difficulty in a problem. It just makes the numbers unnecessarily large, right? It doesn't really test the concept we're trying to get at. So this is usually the biggest one that you'll see. Okay, so that talks about perfect squares a little bit, but now we've got to talk about perfect cubes, the other side of this. So in junior high, you probably dealt with those 2D and 3D shapes as well, but this is the more abstract part of it, not necessarily the concrete physical shapes of cubes and squares. So 216 is going to be a perfect cube. 6 is its square root because, so there's another way we can relate those two numbers, and we can say that 6 cubed is 216. So if I take 6 and multiply by itself 3 times, that'll give me 216. This isn't saying 6 multiplied with 3 is giving me 216. Remember what that exponent actually means. It means you're taking that base, multiplying by itself 3 times, okay? So we'll define a perfect cube very similarly how we defined a perfect square. So we can say that a perfect cube will be the product of a number multiplied by itself three times. Okay, that 3 times is very, very important because if I don't have that 3 times in there, that'll be technically it's a perfect square. Okay, a number just multiplied by itself. Now cube root, very similarly, we're going backwards. So we're looking for a value that can be multiplied by itself again 3 times to give the original number. Almost the same definition. Just remember that for perfect cubes, you need that number to show up 3 times, where perfect squares is only twice. Okay, we'll list the first 10 perfect cubes. Also, the reason why we only go to 10, the numbers get really large really fast. And you can imagine this because you're multiplying that number by an extra time. Remember, a perfect cube is 3 times. The numbers are going to grow really, really quickly. So we'll do the same thing that we did before, just in the chart. Okay, original, and then cube. It's not a very good looking 3. Okay, cube. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Same thing as before, 1 cube. Now your calculator actually has the ability to help you out here. So you could put in 1 times 1 times 1. And that would do it. You should also see a little exponent button. If you've got a graphing calculator, it doesn't matter if it's the 84s or 83s, they're all very similar. And many other scientific calculators have this exponent button also. It just might look different. So you have to check your owner's manual, the instructions, whatever it is, to find out which button order you actually have to press. But for these ones, you can actually press the 1. That little button above the divide that looks like triangle, you could press that and that will tell us we're putting something in the exponent place. So we're going to put in that 3. So this is now saying it's 1 cubed. Okay, enter, I get my 1. Now we can test it out for 2. 1's not very interesting because it's just a bunch of 1s and obviously that doesn't change anything. So 2 times 2 times 2 gives us 8. And we can test it out with our exponent button also. So 2 to the power of 3 is what this is telling us. That is going to give me 8 also. So however you choose to do it, go right ahead. I'll give you the same thing. So I'll rattle these ones off. So we'll get 27, 64, 125, 216. And you can already see the numbers getting really large because I think for the squares we ended at 225. So this is 343. 8 cubed is 512. 9 is 729. 10 is 1,000. You can see they get really large. So for perfect cubes, you definitely won't see anything bigger than 1,000 because, again, it doesn't really add to the complexity of the question. The difficulty doesn't make it. It's not any higher. It's just more tedious because the numbers are larger, okay? So it'll only go up to 10 usually for perfect cubes. And this is the one where I'm not going to do all of them, because as you can see, there's quite a few of them. So I'm going to pick and choose the ones I think that are super important. And again, in the full keyed version that you'll see up on the video after, you'll have all of them here. So if you want to try them out, by all means. So we're going to talk about A. What else did I want to do? I wanted to do F, J, K, N, and O. So I'm going to do those ones. Now, it seems like a lot, but I promise they're relatively quick. So we're asked to determine whether or not each of the following is a perfect square. If it is, determine its square root without a calculator. So we'll talk about some of those estimating techniques, because some of them won't be perfect squares, right? So we'll just start working our way down. So we'll start with A. Now, I'm looking for the square root of 16. Now, remember, a square root means it's a value that I can multiply by itself to give us that original number. That original number I want is 16. Now, when we talk about radicals, we're going to give that number a name. So we'll hold off on that for now. But we're looking for a number I can multiply by itself to give me 16. Okay, so I can just start trying some numbers. So 2 times itself obviously won't work, but I know that 4 times 4 will give me 16. So I know that the square root is going to be 4. Okay, now here we're talking about the principal root, because I know there's some of you out there that might say, but wait, what happens if I use -4? And I can do it. -4 times -4, those are 2 rational numbers that I can multiply by itself, and that still gives me 16. Here we're going to assume something, and we're going to assume that we're dealing with the principal root. Now, the principal root is the one, let me write this out here first. Principal root is the one that's positive. Okay, we're going to deal with the one that our calculator tells us, because if you notice, I actually do have a square root button. It's very tiny. It might be difficult for you to see, but it's the one that kind of looks like a check mark. Okay, so if I put in 16, my calculator will tell me the principal root. It won't actually tell me that -4 is technically a root here also. Okay, so we're dealing with the principal root here, the positive sign one. Okay, so just keep that in mind. Okay, so 4 is going to be the square root of 16. Now for F, if I tried to do that, I know 19 isn't a perfect square, and I can double check our chart because I know 19 doesn't fall on here at all. But I can see that 16 is on there, and so is 25. And that's going to be really important to help us estimate. So if I try to do the square root of 19, I know that the square root of 16 and the square root of 25 fall on either end of that value. Okay, so I know that if I'm going to do the square root of these, square root of 16 is 4, square root of 25 is 5. So I know that the square root of 19 should be in between 4 and 5. Now, I'm not exactly sure where, if it's 4.1, 2, 3, 4, 5, whatever. Now, if I look at how far that the 16 is away from 19, that's 3 numbers, 17, 18, and 19. But if I look at that on the case of 19 to 25, that one is 6 numbers away. There's a bigger gap in between 19 and 25. So to really illustrate that point, I'm just going to move this over. I'm going to make that gap actually look a lot bigger. So I know that it really can't be 4.5 because that would be somewhere over here. Okay, it'd be a little bit closer. That gap between the ranges, the gap between the numbers should be a little bit closer than it is 3 and 6. So I know that the square root of 19 should be less than 4.5. Since 19 isn't halfway in between 16 and 25. So now I don't exactly know where, but we can estimate it. So if I know it's less, maybe we'll say it's around 4.3-ish. So we'll say it's approximately 4.3. And we'll double check it on our calculator. So take the square root of 19, and we'll see that it's 4.35. So we would actually round that up to 4.4. So we were close. And again, it is just an estimate. So take your best educated guess, but this process helps you get a little bit closer. If you can bookend that value by 2 known square root values, you have a way better idea where it's going to be. Okay, so roughly 4.4. My estimate was a bit off, but hey, it is just that, just an estimate, okay? Next one we'll talk about is J here, so the square root of 0. Now we're looking for 2 numbers or a number, I should say, that I can multiply by itself. So 2 of the same number to get the original. Now, the only way that that works is if I do 0 multiplied with 0. That means my square root of 0 is 0. You can check that on your calculator as well. Square root of 0, right there. Okay, it will show you it's 0. K is an interesting case because now I'm looking for two numbers that are the same that I can multiply to give me a negative number. So now we got to think back a little bit to grade 8 integers. Okay, you were taught that a positive number multiplied with a positive number gave you a positive number. Now, a negative number multiplied with a negative number gave you a positive number also. Those negatives canceled. Now, if I need to have two numbers that are identical, so a number times itself, to give you a negative sign, you were taught the only way to get a negative sign was a negative multiplied with a positive. Those are technically two different numbers. This means I actually can't do this. So this does not exist. I can't actually take the square root of a negative number for the simple reason I can't have an identical number multiplied by itself to give me a negative. And if you really are uncertain, check it. Your calculator will give you some sort of error. Here it tells me that there is a non-real answer. So in the real number system, the numbers that you all know, there isn't a way this can be done. But that means there has to be a way it can be done in the non-real number system. But that comes a lot later. There's a whole thing on imaginary numbers. And basically, there's a stream of math that says that you can actually take the square root of a negative number. Okay, but for our real number system, that doesn't exist. And you might see this show up as DNE in the future, just as short for does not exist. Okay, so in the real number system, that doesn't work. Okay, let's talk about a cube root for a second. So I know this is a cube root because of this 3 right here. And again, we'll talk about what the names are of these different parts when we get into radicals a little bit later. But that little 3 on the outside tells us it's a cube root. So now what I'm looking for is a number that I can multiply by itself 3 times, not just 2, to get me that original number of negative 64. Okay, so really think back into integers and what happens when you do negatives times positives times negatives, all that sort of stuff. So I need the identical number. So they either all 3 have to be positive or all 3 have to be negative. Okay, so let's think about those two cases. So if it's a positive times a positive times a positive, I actually get a positive sign. But if it's a negative times a negative times a negative, I actually get that negative sign. Now the reason why is because 2 of those negatives cancel to become a positive. So let's actually show that. These 2 come together to give us a positive. Now that positive in red multiplied by the negative that's left over in blue, that gives us that negative sign. Now I know I need to have a negative 64, so I can't have the top case, which means that I can actually take the cube root of a negative number. Because if I have 3 negatives, 2 of them cancel, give me a positive, but the leftover one always changes it back to a negative. So I can do this, I just have to figure out the value that makes it possible. So if I think back to my perfect cube chart, and I can even go back and look, 64 is on it. Okay, and its square root is 4. That must mean that if I start by doing negative 4 times negative 4 times negative 4, I'm actually going to get 64. But remember what we said about the negative signs. This is going to give me negative 64. So the cube root of negative 64 is negative 4. And this one does work. For O, the last one we'll talk about here, you're going to see that's still a cube root. However, my 27 is positive. And what did I just do to this? Doesn't look any different for you. Oh, there we go. I fixed it. So that 27 is what we're going to be trying to get to. But now we're in the top case here. Positive times positive times positive to give us that positive sign. So I need to think about the cube root of 27. So 1 cubed won't do it. 2 cubed is a 8. And 3 cubed, that'll give me that 27. So I know now that this is a perfect cube with a cube root being 3. And you can try all the other ones as well, and I'll put the answers in that's filled out solutions copy just so you have them. But that's sort of the process we're going to go through. Excuse me. So if we look at example 2, this is a little bit different. And again, I won't do all of them. I'm going to do the top 3, so A, B, and C. And I'm going to leave D, E, and F. I know the numbers are larger. The process won't change. So for A is where we'll start. We're asked to determine which of the following are perfect cubes, which ones are perfect squares, which ones could potentially be both. So let's start with A. Now, we did something last time called prime factorization. So we talked about a factor tree and the division algorithm we came up with. So take your pick. It doesn't really matter. I'm going to do this one just using the factor tree. It just looks kind of nice. So we're going to break this up into two factors. And I know that it's divisible by 5 because I end in a 5. So my other number here would be 25. Split that one up. 5 and 5. 5 is prime numbers, or 5 is a prime number, I should say. So there, I know I'm done because I've gotten down to my prime factors. So I'm going to rewrite this as that product of prime statement. So 125 is equal to 5 times 5 times 5. Now, if it's a number multiplied by itself 3 times, we know that's a perfect cube. Okay, so 125 is a perfect cube. Can't really be a square root because there's no way to match up these factors in a way that I have a number times itself. Since I have 3 distinct factors, there's no way to make them 2 equal groups. So I can't actually say this is a perfect square, but yes, it is a perfect cube. Okay, so let's talk about 64 now. This one might be a little interesting. Again, we'll factor it. So let's use that factor tree idea again. And I'm going to start by splitting this up into, what do I want to do here? Let's use 2 and just keep it simple. So 2, 32. And we'll do 2 and 16. We'll do 2 and 8. We'll do 2 and 4. And then we'll do 2 and 2. So as you can see, all of my prime factors happen to be 2. So again, we'll write this out as that product of prime statement. So 64 is equal to 1, 2, 3, 4, 5, and 6, I believe. 1, 2, 3, 1, 2, 3. Yep, got them all. So there it is as your product of prime statement. Now we need to decide perfect square or perfect cube. Now, if it's a perfect cube, you're going to have 3 distinct pairs, in this case, multiplying together. Then they have to be identical. So if it's a perfect cube, it's one thing multiplied by itself 3 times. So let's see if we can break this up in a way that will allow me to do that. So if I group them in pairs of 2s, you can see that 2 times 2 will be 4. So that's 4 times 4 times 4, which I could do. So that's actually, this right here shows that it's a perfect cube. 4 times 4 times 4. And if you don't believe me, there you go, 4 cubed, 64. But now I could also potentially do this in such a way that it gives me a perfect square. What happens if I use 3 2s to make 2 equal groups? Okay, 2 times 2 times 2, that's 8. And 8 squared is also 64. So now I've shown that 64 could potentially be both a square and a cube. So this one is both a square and a cube. Oops. Okay, so you could have numbers that are potentially both. And again, you could do this very, very, very quickly just by putting in the square roots or cube roots on your calculator. However, if you were asked to determine something, you really asked to show how you got there. It doesn't really make sense that you can plug it into a calculator. I know you're capable of doing that. But if you're asked to actually determine something, you're asked to show your thinking, figure out how you did it, not what your calculator is telling you. So keep that in mind. Okay, for 216, we'll do that one as well. So again, let's split this up, start factoring. So 2 and 108, if I do 54 and 2, 2 and 27. Oops. And we'll do 9 and 3, and then 3 and 3. Now you can see I've got 3 prime factors that are 3s and 3 prime factors that are 2s. So we'll write out this 216 as a product of primes. 3 times 3 times 3 times 2 times 2 times 2. Now we're going to try and decide perfect square, perfect cube, or both. Now if I try to do this in 2 equal groups, I have 3 3s, which I can't split evenly into 2 parts. and 3 2s, which I also can't split evenly into 2 parts. So I know it isn't going to be a perfect square. So now we've got to check if this can be a perfect cube. So I can basically think of it as doing a 3 and a 2 together, a 3 and a 2 together, and a 3 and a 2 together. So if I were to rewrite this, I can say that I've got a 3 times 2, and a 3 times 2, and another 3 times 2. I can just rearrange the factors because for multiplication, the order doesn't matter. I can multiply however I want. By doing this, I've shown that it's 3 times 2, which is 6, times 6, times 6. So now I know for sure that 216 is a perfect cube. So 216 is a perfect cube, not a perfect square. So that's the therefore symbol. So therefore, by doing that, 216 is a perfect cube. And again, you've determined this. You haven't stated this. So you've actually shown, using some thinking and some work, that 216 is a perfect cube. Okay, and again, I won't do those last 3, but they will be filled out for you in that solution key. Okay, so let's talk about determining them using that prime factorization, which we actually just did using that factor tree. But here we're going to use that division algorithm, which we looked at last time. And again, I think I'm going to do only one of each of them. Okay, so I'll do one perfect square example, one perfect cube example. But again, you will have the filled out version for you should you wish to try them on your own. Okay, so perfect squares will have prime factors that occur in pairs. Okay, so you're going to see the same things repeat as we do this. Okay, the square root of the original number will be, and I have to make a little edit here. I wasn't fond of how it's worded, so we're going to cross that part out, and we're going to fill it in down below. So the square root of the original number will be the product of one prime factor from each pair. So we're going to list out all the prime factors, and we'll see that they end up being pairs because perfect squares have the same number multiplied by itself. And we're going to take the product, so we're going to multiply one prime factor from each pair, and we'll see that we get that square root. So we'll do A together in here, and I'll put B up in the solution. So if we're going to determine the square root of 1296, remember how that division algorithm worked for us. So we made a little bit of a T-chart. We had the primes on one side, and we had our value we're working with on the other, so 1296. So we're just going to start out by listing some primes. So if you just start with 2, we're going to cut that 1296 in half. So 1296 divided by 2, that'll give us 648. I could do a 2 again and get 324. I could do another 2, get 162. We can see that since 162 is still even, we can do another factor of 2. So 2, and that will give us 81. Now we're into the odd numbers. So now we've got I can't use 2 anymore, but I could use 3. And that will give us 27. 3 again as a prime number would work. That'll give us a 9. One more 3 will leave us with a 3, and our final prime factor of 3 comes out to give us that 1, which we want in the end. Now here's our list of primes. Now notice what happened. We did say that they would occur in pairs. So I can see I have a pair of 2s. I've got even a second pair of 2s. So even though 4 2s existed, I can pair them up. Okay, so 2 2s, 2 2s. And then for our 3s, the same thing happens. So there's a pair of 3s and one more pair of 3s. I want to kind of block it. So there's 3, there's 3. Now we said that in order to find our square root, we can take one of the prime factors from each pair. Okay, so we'll take a 2, we'll take another 2, a 3, and a 3. So if I say that I'm going to do, actually let's write this out first, sorry. Let's do the square root of 1296 equals. Okay, we're taking one of the 2s, one of the other 2s, and then a 3, and then the last 3. So one from each group. So you can see if it's all color coded. We're taking one from each, and we are taking the product of those primes. So when I multiply them all together, the 2 times 2 will give us 4, 3 times 3 will give us 9. 4 times 9 is 36. And we can double check just to make sure we determined this correctly. So the square root of 1296, so the square root 1296 equals, and we can see that it is 36, just like we said. So again, when it says determine, you are asked to show a method and prove that you can actually get that square root, not just what your calculator says. Okay, that word's very important. So there's that method done for you. And again, you can give B a try, and I'll make sure it's up in the answer key for you. We're going to do something similar when we talk about cube roots. So if you think about the analogy that we had when we first started this, all those definitions, it's very, very much so the same here. So perfect cubes will have prime factors that occur not in pairs, but in triplets. Okay, so there'll be 3 of them. And I can't spell, so that should be triplets. There we go. The cube root of the original number will be, and again, we're going to alter that sentence grammatically. It just doesn't, not a fan. So we'll cross that part out. So the cube root will be the product of 1 prime factor from each triplet. Very, very similar to how we did the square root. So cube roots work almost identical, but again, just remember that we're working with triplets, not pairs. So again, I'll do A, we'll leave B for you, and you will have the answer. So we're going to do the same division algorithm, so with primes. And here's our number, 728. So away we go, start plugging in primes to divide by. We'll start with 2 because it's even. We're going to get an 864 that comes next. 2, 432 is what you get remaining. Another 2, and you're going to get a 216. Another 2 for 108. Another 2 for 54. Another 2 for 27. Okay, now we're off the even numbers into the odds. So 3 for a 9, 3 for a 3, and 3 for a 1. So there are all of our prime factors listed out. Now we'll try to find out what our triplets are. So 3 2s go together. Conveniently, I've got another 3 2s remaining. And we also have 3 3s. So there are our 3 triplets. 3 2s, 3 2s, 3 3s. Now the way this works for a perfect cube, because we are trying to do the cube root here, so the cube root of 1728 is going to be equal to the product of 1 of each of those. So we're going to take, let's do this in order, 2 multiplied with another 2 multiplied with that 3, and again 1 from each triplet. So when you actually multiply those together, 2 and 2 give you 4. 4 with the 3 that's left gives you a 12. So let's double check to make sure that our math is correct. So let's find that cube root function. If you press math 4, that'll bring up your cube root. So 1728. There you go, 12. And you can even go the other way, 12 cubed, 1728. So we know we're good. Okay, again, it does say determine. Okay, so really, really make sure that you're using a method that you can show on paper to someone reading this to actually say that, yes, you can determine this, not just state what your calculator says. That's a very different question. Okay, now if this is multiple choice, numeric response, of course, you don't have to show your work for something like that. But if it is written and you are asked to determine, showing that work and that thinking process is important. Okay, last one in here, we're going to use that to solve a problem. So a cube has volume of 4,913 cubic inches. Okay, what is the surface area of the cube? Now, these formulas you learned in junior high in grade 9 when you had to do volume and surface area of 3D and 2D shapes, when you did regular area for 2D, surface area for that 3D object. So you did learn that the volume of a prism is the area of its base multiplied by how tall it is. Now, if it's a cube, its base is a square, and its height is basically a length, which is the same dimensions as the length and width of that square. Like all of the dimensions are the same if it's a cube. So you can say that it's the side length cubed. That will give you the volume of your cube. If it's a surface area formula, though, because those are different, remember that if it's a cube, all of the 6 faces are the same. So you're really going to say for surface area that your formula is the surface area is equal to 6 identical faces, where the area of one face is that side length squared. So the cubes are nice because all the dimensions are the same. Okay, so let's start by finding out, well, plugging in some stuff I know. I know I have a volume, so I'm going to start with this volume formula. So 4913 equals S cubed. Now, I don't want S cubed, I just want S. Now, in order to get rid of that 3, I have to do its opposite operation. Now, the opposite here, I can't divide by 3. That's an exponent. The opposite operation of an exponent is the root. So if it's a square root, I would be, or if it was a square as an exponent, I'd square root both sides. But since it's a cube, we're going to cube root both sides. So I'm going to take the cube root of 4,913. And that's going to be equal to S. So I actually have to figure out what the cube root is here. Now, it doesn't actually tell me to determine that cube root. It actually just asks me for the surface area. So here, we could use our calculator. But I'm going to stick to showing you how to determine it by hand, just because of what we've been doing so far. So let's use that division algorithm. 4913. Here are our primes. Now the number seems large, but we can kind of get into a little bit of a, just logically think this out here. I can't use 2, obviously, because this is odd. Now I can't divide it by 3 either, because I can just check, right? I can't divide it by 3. My next prime that comes up is 7. Not divisible by 7. Next prime is 11. Let's try that. That doesn't work. So I've got to try one more. And next prime up is 17. And that one works. So 17 is a prime, 289. Now, if this is going to be a cube, okay, that means that this should be a perfect cube if 17 is one of my primes, which makes sense because I'm told it's a cube, so I know the length, the width, and the height should be all the same number. If I found one of those primes as 17, there's a very, very good chance that I could divide by 17 again, and there you have it. So 17, 17. That means I can do this one more time to get my 1. So my 3 primes are 17. That means the perfect, or the cube root of 4,913 is 17, because you're going to see 17 times 17 times 17 if I were to write out that product of prime statement. So now we can go back to our original formula, and now we know for sure that this is 17 inches. Okay, one side length of that cube is 17 inches. Now that I know that, I can do my surface area. Now that I know the side length of one of those faces, I can plug that 17 in. So that's going to be equal to 6 multiplied with 17 squared. So my surface area here is going to be 1,734 inches squared, or square inches, depending on how you write it. So just remember the units, because I was given them, so I have to use them throughout. So there's your surface area. Okay, that takes care of all of our perfect square, perfect cube type problems before we actually get into exponents in the next one. Again, please check the description there for the blank copy if you wanted to follow along or try some other ones on your own. You will have the solutions ones there as well. And again, if you do have some questions, ask your teacher. Feel free to send me an email, leave a comment down below. Tell your friends about this, to get my numbers up, all those good things that you know and do all the time. So we'll see you, I guess, in the next lesson. We'll start talking about, I believe it's exponents and all those exponent laws. And of course, it just gets more challenging because, of course, math will get more challenging. Okay, so we'll see you in the next video.